All right, so we're going to do this again. We're going to change the numbers. Make it happen. So in this case, what we're going to do is let's talk about release. People who are released to a halfway house. And so we're talking about how many number of subjects, and what we're looking at is how many job interviews do they get. And so we're going to make a list here of the number of interviews. It's going to be 1, 2, 3, 8, and 10. And then 6, 18, 24, 60, and 12. So I want to know the mean and the standard deviation for the number of interviews. I want to know, should we use the empirical rule? And what are the unusual values? All right, check with your neighbors, see if your neighbors got good stuff.
I got 3.01 or 3.008. Yes. The third or the fourth or the second or the third.
Yeah, I think he wants the, I mean, I don't know how many decimal places he wants.
Yeah, okay. I just wrote it as he says, rounding to the second.
One decimal place. One decimal place for the answer, because our data is in whole numbers.
Okay.
So we would go one decimal place to the answer.
So just here. Okay.
What'd you get?
Yeah. Yeah, I got 7.9.
Wait, so is this one? Yeah, this one's right. I got mine.
I do math. I'm also.
Because isn't it just this times here?
So this, I got 120.
Yeah, I got 6.
Yes.
For, so I was taking, because I like 1 divided by 1.
Then for the unusual values, I just got the number of jobs interviewed to be like 1. So like if you got 1 job interview application, then 5%. Yeah.
Yeah, the specific set over the. Okay, so I'm pretty sure.
So wait for the unusual.
All right, so let's see what's going on here.
Yes.
It's not really necessary for us to go out to a lot of decimal places, but
0.1 is
we will for
0.05.
to start with here.
I haven't gotten the last.
Katie, what do you got for a mean?
The number of job interviews, like 1 job interview would be unusual because it's.
Do you have the mean?
Yeah, I got.
I'm not well, so we both are. We got.
Okay, so what you have you don't like? Okay. All right, what'd you get for probabilities, Katie?
We messed that up, everything else.
Oh, yeah, well, yeah, okay.
We did the lines.
Oh, all right. Well, that'll make things not so good. Liz in the back, can you tell me what you got for the mean?
For the mean,
Yes.
5.95.
Okay, so the mean is 5.95. You get all the probabilities, multiply them, and add all those up, you should end up with 5.95. All right. Now, if you know your probabilities are wrong, then yeah, but let's just see if we got more of that. Liz, what do you got for probabilities? Can you list those off for me?
Yeah, 0.05, 0.15, 0.2, 0.5, 0.1.
Okay, so there we go. So this would then be the probability distribution. So it tells us, in a sense, the percentages of how many people had the given number of interviews. So we would say 50% of the people had 8 interviews. That's what that would tell us. All right. So let's see here. Mariah, you got standard deviation?
3.01.
Okay. Now, technically, we would not really need to go out to that many decimal places because our data is only in whole numbers. So we would just go to the 10th place. So this would be basically 6. This would be basically 3. So then the question is, does that number 6 make sense to us? Crystal Wright, what do you say? Is the number 6 a reasonable average here?
Yes.
Why?
Because the math makes sense and it's like within the number. It's within the range from 1 to 10.
Okay, it's within our range from 1 to 10, and that is the data that we're interested in. And if we notice that 8 is where we have the most data, but we certainly have data which is less than 8. And so that would bring it down then to be 6, perhaps. Okay, So then if we say, what does that 6 represent? It would be the average number of job interviews per person. That's what that number means. Okay, question.
So I'm confused how you got that for the standard deviation.
Okay, so then when we do our x squared times all these probabilities, we would be taking 1 squared times this, which is 0.05, 2 squared times this, which would be 0.6, and so on. We add up all those numbers, we would end up with 44.45. That would be the total here, once we add all those up. So then the standard deviation would be the square root of 44.45 minus 5.95 squared. And when we do that, we get 301. Okay? All right. So far, maybe? So, Rachel, should we use the empirical rule?
No.
No. All right. Can you tell me what would be the unusual values, Rachel?
That first one.
Which would be 1. Okay. Hillary, how would you phrase that?
You would expect, or you would be surprised if someone had one job interview.
Okay. We would be surprised if someone had only 1 job interview. We would expect them to have more than that. Okay. Now, if you're paying attention, you'll notice that it took us a lot less time to do that than it did to do it the first time. Why? Because we had just done it a few minutes ago. And you knew pretty much where all the answers came from. Why? Because more than likely you did not look at the previous day's formulas and procedures before you did it the first time. But after we did it, you pretty much knew how to do it, right? So what that means is, I'm going to talk about stuff now for about half an hour or so. And then when we get together on Thursday, you should look at what we did today so that you will know how to do the stuff when I ask you how to do it on Thursday. Okay? So this was a lot faster. It's not easy, but once you do it a couple of times, the math is not really that hard. Okay. So now we're going to change our situation, and we're going to be, and I'm pretty sure my camera's on. Yep. Okay. So we're going to talk about a situation where we need to understand what is being measured. Just like what we just did, and just like the other things that we had. We asked the question, what is being measured? And the thing that is being measured is the number of people saying yes. Okay? Now, it might not be people, it might be children, like that, or whatever. But it is more specifically the number of items in a specific category. Okay. So, let's just say that we have 30 people. And we ask the question, did you go to a water park last year? I want to measure how many people would say yes in that situation. So what are the possible values for my measurement? What would be the smallest number? 0. What would be the largest number? 30. And I'm going to represent that with the letter X. X could be any number from 0, 1, 2, all the way up to 30. Okay. Now, how many people did I ask? I asked 30. I'm going to use this N is equal to 30. Okay. N would be the sample size. Okay. How many people I asked? And I want you to understand the difference between two different things. I have what is called the sample proportion. And I also have the population proportion. The sample proportion, I put a P with a hat on it. I call it P hat. And that is X divided by N. All right? So how many of you went to a water park last year? 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let's say 18. So this would be 18 out of 30, which would be 0.6. That is the sample proportion. Now, it's good for me to know that, but what I'm really interested in is the population proportion. And that would be if I had, let's say, everybody in La Crosse. And if I were to ask them, how many of you went to a water park? That number would probably be different from this, right? So let's just say that it would be 40%. So I would say P is equal to 0.4. Now this number has to be given to me separate from my own observation. Somebody would have to tell me that the population proportion is 40% or 0.4. There's another word for this, and this is the general probability. The population proportion, or the general probability, has to be given to me as something that I know ahead of time. And then the entire idea here is I want to figure out the chances for all of my X values if I know what my general probability is. So what am I trying to do? What is being measured? The number of people saying yes, or the number of items in a specific category. And what will I calculate? the probability of X. The probability of getting a certain number of responses, but I have to know this probability ahead of time, 0.4. Now, I'm going to show you where this comes from, and then I'm going to show you the equation that we use to calculate. If you remember, I'm going to do a tree diagram, but I'm going to do it vertically instead of horizontally. So I'm asking the question, yes or no. And the chance of being yes is 0.4. The chance of being no would be, unfortunately, 0.6 over here. How do I know this value? That's 1 minus the probability of yes. Every time I would ask somebody, based on the general probability, I would say there's a 40% chance of them saying yes. And then I'm going to call this thing Q, 0.6, which is 1 minus Q. 40%, this would be the probability of yes for each person. This would be the probability of no. So I'm looking at the situation, and I'm not basing it on my observations. I'm just thinking, what will happen when I ask people the question? And I look at it and I say, okay, it could be that they went to a water park or maybe not. But if the general probability is 40%, then that means 40% yes chance, 60% no. That would be for one person. But I'm not just asking one person. I'm going to ask a lot more people. But every time I do it, it splits up into probabilities. 0.4, 0.6, 0.4, 0.6. And so then if I go through this, I have all these things happening, and I have all these different chances of them happening. Remember that when we do probabilities, and we go from one branch to the next, we multiply those probabilities. So, if I were to ask the question, what's the probability that everyone would say yes? That would be 0.4 to the 30th power. So what's 0.4 to the 30th power? Well, let's see. What does your calculator tell you? Do you have a nice number? No. Basically, 0. You probably have something in scientific notation. If you have something in scientific notation and it has a negative exponent on it, that means it's a small number. Emily, you got that number?
You know, the whole thing.
I do.
1.152921505 exponent of -12.
Okay, so this is a very small number because it has 12 decimal points over from here. So it's really, really small. So that means it's basically 0. So if I had a room of 30 people and I said, hey, did you go to a water park? I would not expect everyone to say yes. But then the question is, What about 29 or 28 or 15 out of 30? How would I know all those possibilities? I have to have some way to go down every one of these branches, multiply all these probabilities, and then figure out how many people said yes with all these branches. And it's 2 to the 30th power, which is a lot. So I'm not going to be able to do that. But there's a formula. And the formula that we use, it's in our textbook. It looks like this. Okay. So when we see this and we say, okay, what's going on here? As it turns out, there's an easier way to make this happen on your calculator so that you don't have to go through all these steps. So I want you to know how to do this so that it can be relatively easy for you. And that is, what is this thing right here? This whole thing, which has all these exclamation points. I'm just going to show you what that means. N factorial, that's the name of that, is n times n minus 1 times n minus 2 all the way down to 3, 2, 1. It's there, but you don't have to use it. Okay? We're going to talk about a different way to make this happen on your calculator to make it quite a bit easier. So what we're looking at here is I have to know what I'm talking about. We're going to do an example. We're going to ask the question, for example. What would be the probability of having 20 people say yes? So I'm going to look at this and I say, all right, if I know that 40% of people have done this, then what's going to be the probability that 20 out of those 30? What I have right now then, x equals 20, n is equal to 30, p is equal to 0.4. And when I'm looking at this formula, that first part, this section right here, I'm going to look on my calculator for NCX, or some calculators NCR. That number is telling me how many different ways I can make the combination. So I want you to look on your calculator. You might have a PRB button or some other kind of probability button, or you might just have this button. And I want to know, what is 30C20? I want to know the answer to that question. So I want you to look on your calculator, see if you can find that place where it actually gives you that information. And it's going to be a pretty big number. Okay. Okay, Crystal Reed, did you find it? Okay.
I don't know how to use my calculator. I found it.
Okay, so what you're gonna do, you're gonna hit 30. You're gonna hit 30, and you're gonna hit that button. Over there. Enter. And you're gonna hit 20. Okay? Most calculators, you would make 30, hit the button, make 20. All right? Sure.
Did you find it yet?
Yes.
Which one was it?
There we go.
PRV. Okay.
Yeah, I can't find it.
Math.
Oh, okay.
Math. Okay, Crystal, right? What do you got? You got a number? Not yet?
No, I'm writing down how to use calculators.
Okay, that's okay. Oh, you got a number yet? Got a number? Okay, 30. 50. Okay. There it is. All right.
Okay, yeah, I have to change mine.
So here's how this works. In order to put this into your calculator, you're going to do this. Okay. This is P, 40%. This is Q, 60%. This is X, 20. This is N minus X. So you're going to put this into your calculator. See what happens. So I'm getting 0.001997. That's approximate. Okay. So what I want to do is I want to make sure that you're actually getting this number. If you're getting this number, then we're good. Now it's possible for me to go around the room and say, did you get it? Did you get it? Did you get it? Did you get it? But I'm not going to do that. I'm going to say, if you didn't get it, tell me and we'll fix it. Right? Maggie. Okay,
Lost. Don't know.
okay, that's the right answer. Okay. So do you know how to get this?
Yes.
Okay, so on your calculator, you put this in,
Yes.
and then you hit multiply by 0.4 to the 20th power,
Oh.
and then times 0.6 to the 10th power. Okay, that's what that symbol means to the power. Whatever button you need to use to make that happen is fine, but that's what needs to happen. All right. So if you didn't get this answer, I want to know, and then I can fix it, okay? You gotta get this answer. Gabrielle. Okay, you know how to get the 20C or 30C20?
Is that like 30 PBR 20?
No, it's not P, it's C. P is a different one. Let me see what you got. Okay. Probability. Go over to that one. There you go. Good, enter.
And then.
Okay.
Okay.
And then you multiply by 0.4 to the 20th times 0.6. Okay.
That makes sense. Thank you.
You're welcome.
Wait.
Yes, the yes and no. Eventually.
And the one I tried to
Okay, then you need to add
But that's what part I ended up yeah, like I did this whole bit. I always look at the example and like, can I figure this out from the example? No.
See? Yeah, that's great. Right.
You're killing me, but you weren't that far.
Right? Any other questions about this process so far? Good. So if you have not yet got this number, I would like to know, and I would like to fix that process for you. Okay. Question?
Like my decimal, this number is like.
Okay. So.
Yeah, so I was like, I did the journals for week 3. How? I don't even know how to journal write.
I need to discussion board for this. I have to read.
All right.
If
So
we got to
that
grade it,
is scientific.
I guarantee it's easier.
See how it has the
Yeah.
negative
Okay, so it's like a story, and it's like a
So,
fake story.
just a note for you, because everybody is going to see this every once in a while. You need to understand what this is. This right here is the same thing as 1.997 times 10 to the negative third power. Because if you shift over the decimal point to be after the 1, you shift it 3 places, and it's a small number. Some calculators are set up to give you this in scientific notation. So you have to know how to translate between this and this, because then you have to make it decimal. So if you ever see a negative exponent on something like this, then that means, let's just do an example. If I have 6 times 10 to the negative 2, I write 6, and then I move it over 2 places like that, and it becomes 0.06. So if you see something in scientific notation, you have to be able to make it into decimal form. Question?
Can you explain to us how you got like each of these numbers, like what's Q?
Okay, Q is 1 minus P. P is the general probability of something happening. So once I know that the chance of somebody saying yes is 0.4, then the chance of them saying no is 0.6. Okay? And then X is the number of successes I'm concerned about. So 20 people saying yes, that's this. And then this is 10, that's n minus X. All right. Now, there is in your textbook a table of these things, so that when you go to doing your homework and it says, what's the probability of this amount of things? There are some situations where you can click on the table and just look at, okay, it's 15 people, 10 of them say yes, general probability is 0.1, and it just gives you the answer right away. So you don't have to go through this for every problem. Okay, the table will make life a lot easier for you. So you should use the table, right? Then, I am going to show you the two easiest formulas you'll ever see. And they are the mean, standard deviation. Once again, the question is, what is being measured? The number of people saying yes. Okay? So I asked the question, for 30 people, did you go to the water park last year? What is the average number of people who would say yes? And it is n times 12. So that's 30 times 0.4, which is 12. What is the standard deviation? It's relatively simple. Standard deviation is the square root of NEQ. So this is the square root of 30 times 0.4 times 0.6. So on your calculator, making sure you know how to do this, you take 30 times 0.4 times 0.6, and then you take the square root of that number. You should get approximately 2.7 or 2.60. Now, I want to give you a graph that will hopefully help you see what we are actually talking about here. What is it that we are actually measuring? We are measuring how many people we expect to say yes. Okay? So, what does that really tell me? If I ask these 30 people, will all 30 of them say yes? No, because we figured that would be basically zero, right? Would nobody say yes? Well, that doesn't seem to make sense either. So what does this actually look like? It looks like this. If I have 30 people and I know the general probability to be 0.4, then the average would be 12, which would be this right here. So if I look at this and I say, I've got a room full of people and I'm going to be talking about water parks. And if I know my general probability is 40%, then I would say, you know, I kind of expect that 12 out of these people have been to a water park in the last year. But it doesn't have to be 12. It could be 13, 14, it could be 10, 9, it could be all kinds of different possibilities here. 12 does not tell me exactly what to think. but it's the average number of people who would say yes. If I did the same presentation to another group of 30 people, it might be 16, it might be 8. But on the average, I would expect 12 people out of the 30 to say, yes, I will go water park. That's the limit. Is it reasonable to say that I would get 20 people? No. That's a very small probability. That's this little pink dot right here. Now, once again, this is how it normally works. I go through, I show you the formulas. It's not easy for you to remember how to work with the formulas. And you have absolutely no idea what else I'm talking about, which is okay. The main thing to focus on first, can you put the numbers into your calculator and make it work? And if you can, then we'll work more on the understanding as time goes on. But to start with, you need to be able to use your calculator to find these different probabilities, and you have to be able to recognize. N is the number of people, P is the general probability, and X is the number of people who say yes. And then those easy formulas for mean and standard deviation, once you recognize the XN and the P, you'll be okay with those two. All right, so this is what we're going to do.